Hello everyone. Tonight we are going to be doing a design exploration of 4481's 2022 robot. We started doing these last year where we basically just pull up the CAD of another team's robot and we start looking through it. So I kind of saw some of the development of this robot. 4481, the Rembrandts are a open alliance team, so we've been able to kind of follow along with their project progress throughout the year. So I know a little bit about how this robot was performing and kind of how they were going about doing testing, but I haven't put in any time going and actually looking through how they manufactured a lot of their parts or how everything gets assembled or what their CAD looks like or anything like that. So we're going to do it kind of live tonight, just going through and seeing subsystem by subsystem through all of their mechanisms and seeing how they went about building their robot and seeing what we can learn from it. So first off, we can start looking through and we can see they have the different mechanisms kind of slotted out here in Onshape. And so I'm going to go through and I'm going to hide everything but the drivetrain. And so that'll be the place that we start. So the Rembrandts have a very unique requirement compared to most teams, in which they are a team from Europe. So to compete, they have to fly to every one of their events. So I believe they did 2 events in Florida this year, and then they were also at Championship. So they have to design their robot to be very, very small so it can actually fit into checked baggage. So they have it designed to both be small and to be able to be disassembled and kind of modular so that they can take it apart between events and travel with it. That also gives them somewhat of an advantage because they have to be able to take it apart, they're able to upgrade their robot really easily because they kind of design it into these modules. So looking at their drivetrain, it is kind of the first thing we notice. It's a relatively standard FRC tank drive, 6 wheels, the same kind of rough top conveyor belting tread that we use on our swerve modules and a lot of teams use. But the biggest thing to take away is as you start figuring out the scale of it and you see how big the battery is and some of the motors, is you realize how small it is. So from the front to back, this is 23.6 inches long, so it's under 2 feet long, which is very, very small. Width-wise, it's 21.6, so it is under 24 by 22. So that is a really tiny robot. For comparison, our 2022 robot was 27.5 by 25.5, I think. So we're about 3 inches bigger in both dimensions, which is a lot of volume when you add it up. And our robot's pretty tiny. So you can get even bigger than that, right? So the max frame perimeter of robots this year was 120 inches. So in reality, you could be about a 30 by 30 square. And they're choosing to only be 24 by 20 by 22 of that. So that is definitely small. Okay, the other part of how they go into designing their robots is they use quite a bit of sheet metal manufacturing. So all of these individual plates here start out as flat sheets that are all cut out. I believe their sponsor is laser. So they have a sponsor who's able to laser cut metal, and they are able to go through and cut out all of these holes. And then after it's cut out of that flat pattern, it goes through and has all these bends put in. So this is how Spectrum used to design a lot of our robots. So our 2014 through 2020 robots all had a decent amount of sheet metal on it. Our 2022 robot was the first year that we didn't have sheet metal on a robot, or like sponsored cut and bent sheet metal. But it does allow for really easy manufacturing because you're not having to necessarily make all of the parts. And it can be done on kind of industrial scale equipment. So almost all of a large portion of this is almost probably all cut out of a single sheet. So they're able to run that operation basically at one time, cut all of the parts. It does take a little bit more for the sponsor to go through and bend them. but it's a lot easier on the team because it can be happening while the student members of the team are doing other parts of the design, doing other parts of testing, while the manufacturing of the drivetrain and everything is happening normally at a mentor site or at a sponsor site. And we've definitely gone through this in other videos when we talked about sheet metal, but the reason why all these bends are here is it allows you to use a very thin material and still add strength. So as you bend it, it becomes much harder to deform these plates. If you just had a flat plate like this, it'd be really, really easy just to push in and bend this in a lot of different places where it's not supported behind it. But because we have all of these flanges, you can't fold this long piece of sheet metal anywhere because of these bent parts, these flanges that give it strength in that like opposite direction. So that works really well. I think most of this is a pretty standard way to do a sheet metal drivetrain. We kind of have these box sections where you have this flat plate and these 4 flanges on each side, and you do those 4 times, once, twice, 3, and 4. It's possible that these are even, it's almost likely, so you see like all of these extra holes over here and extra holes over here. This is so it's all mirrored, so they can take this plate and just rotate it around and put it over on this side. It also lets like your bends be mirrored. There's a lot of simplicity in having things be really symmetric in sheet metal. It makes it a lot easier on your sponsor doing the creating for you. So you can see a lot of those where you have some extra holes and things, but those extra holes are there just to make the assembly and kind of the manufacturing easier. Then you have a front and back end cap. So this is what I'm going to call the rear. So we're going to call the intake of the robot the front. So this would be the rear of their drivetrain, and it just kind of a C channel that goes over those 4 plates, kind of bolts everything together. And then you have a front plate that does the same thing, but with just a little bit of a lower cutout here and some reinforcement inside of there to let the ball come up over the frame between the bumper gap that they have in the front of their robot. One of the things I don't know how they did, so we have this tube right here, which is more than likely a piece of extrusion, so just like a box tube. But I don't know what's inside of it, so we can find out. Maybe we can find out. So, oh, maybe nothing. It might just be riveted straight in. Yeah, so that's probably just a tube that's going to get riveted in from the bottom, and get riveted in across this front rail, is my guess, and riveted into the flanges here. And that's just going to be to help support this flange and this opening so that if it gets run into, you're not kind of denting this piece of sheet metal. It's pretty thin in, right? You wouldn't want to dent that. So that's 0.079 inches, so 0.08 inches. The other thing to remember about 4481 that's a little bit weird as you're going through their CAD ever is because they are a European team, a lot of the stuff sometimes is metric, so the dimensions may not always make sense when we're measuring in imperial units. But for us learning from them, that shouldn't affect anything. But if you were to like copy things from their CAD directly, you may have to go through and change pole sizes and different fasteners and things back to standard or whatever fasteners you're using on your team. Okay, so what are some other cool details? I don't want to spend too much time on the drivetrain. But they do have some cool things. So this is a really cool thing, and there's been a few teams doing this concept in different ways. But all 6 of their drive wheels are dead axles. So they have these bolts right here. So it's just a socket head bolt, and it's running all the way through to a nut on the other side. So this is the same concept of how the outer wheels on the kit chassis works. You have those like 3/8 bolts going all the way through, and then the wheel itself is spinning on bearings. Theirs is a little bit more, is a little bit different from the Kitbot because not only is it a dead axle, it's also what's called a tube axle, I believe. Let me see if I can verify that. Yep, so we can hide that spacer. So this right here is the tube that's going through. So this tube is separate from the bolt. So there's a whole wheel assembly. Let's see if it, I don't know if Onshape pulled it to where it can show up as a sub-assembly or not. I'm guessing it. Oh, yeah, it does. Okay. So if we isolate this, we can get all the way to seeing just this wheel assembly. And so if you pull this bolt out, this whole wheel assembly will drop straight out of the robot. So it makes it a lot easier to swap wheels. The sprockets are bolted into the wheel itself. And so you can get wheel swaps really quickly. If something happens, you damage a tread or you damage a wheel, it's really easy to change. You don't have to worry about like kind of the spacers and everything stay together. If you do it on the kitbot, it's sometimes a little finicky to get the spacers in the right spot as you're trying to put the bolt through, because all of the bolts and the bearings and everything ride directly on that bolt. Where in this case, the shaft for the wheel is stays with the wheel and the spacers and everything, and the retaining bolt, the shaft bolt that goes all the way through, is separate. This also lets you make a stronger chassis because you're able to compress completely on this spacer, and you're able to fully tighten this bolt down. You're able to, once you tighten it, you get what's called preload, and this whole assembly gets very, very stiff because of the amount of compression that's going through onto this shaft. So they've definitely, a lot of teams have been doing this for a lot of years, and you start getting cooler and cooler little innovations to make it easier and easier. And so a couple of the things that they were able to do are things like these little plates. So there's one here and here on the other side. And what these allow you to do, I think the first team I ever saw do it, I think was Hot, quite a few years ago, probably 2014 or 15, or maybe even earlier than that. But versions, things like this have been done. I think 11.14 did things like this as well on some of their sheet metal drivetrains. But these little plates let you center that tube axle and it gives you a positive kind of locating point for it when you're sliding it up and in. And that makes it a lot easier for you to line up this tube with the hole that the bolt has to go through. So if you don't have that, sometimes it can kind of get off at an angle when you try to like stick it through, and it just takes a little bit more time. So a lot of that is just there to make it easier. It also prevents any sort of sliding or shifting while you're trying to assemble it. And it's a very nice, convenient feature to upgrade that. It makes it so you can't push it up too far. Changes the loads a little bit. So if you really put a lot of shock load through this and you somehow go past the preload on this, or if this isn't quite tight, this will run into this plate up above. So it's not just trying to shift or bend the bolt or anything. It'll kind of get stopped a little bit on its own. It should be a little bit, just in general, just a little bit better. The other part that we hinted at before we went into that whole explanation is this, what I'm guessing is 3D printed, almost certainly 3D printed. This right here is kind of the opposite of this plate. And so on the inside, this is here to actually hold the nut in place. So this holds the lock nut for this bolt. So now when they need to drop the wheel, they don't have to get a wrench in here to hold this nut at all. It's already bolted. Basically, they're bolting the wrench into place, which is this 3D printed part. And so they can just come in with a wrench or a drill, unscrew this, the nut stays there, and the wheel can drop in and out. So that makes it really convenient. It's a feature that just helps when you know you're going to have to maintain your robot, when you know you're going to have to work on it, especially if you're going to have things mounted up and above, right? It's very easy. Once I add back in the rest of the mechanism on top of this, it gets a lot harder to get a wrench into here, into the middle of the robot. It's probably doable, but it's not something you want to be doing all the time, especially if you're doing it potentially between playoff matches or something like that. Features like this that help you maintain the robot better, help you do repairs faster, anything like that eventually leads to you being able to win more events because your robot's more reliable and you're spending less time fixing it. Awesome. Okay, so a couple last details we didn't go through. relatively standard gearbox, it looks like. It's just a single speed 4-motor gearbox. They're using Falcons. They have the pinion gear, driving the gear here, and then they get a second reduction from their sprocket assembly. So they have a small sprocket here and a big sprocket here, so the wheels get to be spinning even slower than the sprocket shaft like we'd want. They're running number 35 chain, which is normally a good idea. It means you don't have to worry about chain tension as much. So that's actually one of the things you can look into their system or into their drivetrain, and they don't have a way to tension the chain at all. So there's nothing that allows them to slide a wheel or anything, or kind of change the distance between the wheels like you would do on a kind of a standard West Coast drive where you have 25 chain. You normally want to be able to like slide the blocks, or depending on how you build it, you normally have some way to slide the wheels a little bit to change the chain tension. In this case, they don't, because with 35 chain, you can normally get away with it. If it's getting to the point where the chain is stretching so much that you think it's loose enough to where it actually needs to be replaced, you probably just replace the chain, and now you have a new tight chain again, and everything works. But you don't really, it's much harder to have it actually slip off with 35 chain just because the sprocket teeth are so much bigger. Another one of the things they did, and I'm not sure if they actually just did this in CAD or if they actually built it this way, but they have the extra sprocket on their outer wheels. And so if they did that, if they actually did build it that way and it's not just a CAD situation, this allows them, it's a little bit more resources, because you have these extra sprockets that you're paying for, but you don't necessarily need, because they're just sitting here, they're not powering anything or doing anything. But what it potentially allows them to do is reduce their spare parts numbers, right? Because if they just have extra outer wheels, or if they have an extra wheel, it can go into any of the 6 spots. It doesn't matter which one it is. And so that is often very convenient if you have the resources to do it, and you can just make some of your parts more identical to other ones. You can have fewer spares. That may make it to where you only have to have a single spare wheel like on your cart with you, or maybe if you go through too many wheels, something weird happens, part of your design isn't quite right, and you start breaking things, you'll end up having more spares and having more ways to have a solution than you need. It's also possible that this is just something they left in CAD. It was easier to make one wheel assembly, and the real one doesn't have this, and they have slightly different bolts going into just this one sprocket on the outer wheels. I would have to look at the actual robot to know that. Electronics don't seem that different. Let me see if I can. Oh, well, that doesn't help because it's not the whole assembly. Okay. Let me hide the RoboRio and their little board. So yeah, they have a little. Oh no, this makes it. This because it's upside down. That makes sense. So to be able to see the PDP for inspection, they have a little panel right here that they're able to take on and off, and has all their breakers on it, and so they can get access to it from underneath. So they're not trying to pick up the RoboRio or change the wiring of their robot, or anything like that, or move stuff out of the way to be able to fix the wiring. They can do a lot of it from underneath if they need to. So this allows them, this is one of the tricks they're probably using to be able to have such a tightly packaged robot, is by using some amount of access from underneath, instead of having to try to move things around and fit everything up above. You can fit things on top of each other a little bit more if you start doing things in more than just looking at it from above. Last little bits, we have the compressor mounted just with another bracket to let it be 90 degrees and fit under kind of where the ball comes up. Their pneumatics hub for controlling the pneumatics things. Relatively kind of standard battery box. Looks like they have a strap going across the top horizontally across the long section of the battery, I guess that's what I'm saying. So it would probably strap in here and go over to this side, have some other place to get a buckle on it. At least that's what it looks like, because it doesn't look like there's another one anywhere. And then main breaker is probably just mounted through something, either a hole there, or they might have another plate that just isn't showing up here currently. Cool, I think that's most everything. Yeah, otherwise it's just a couple different ways to do crossbars. They may choose one or the other, maybe just for mounting or how they're doing their climb. We may look through that as we get up into their superstructures. All right, let's look at the rest of the robot again and see where we're going to go next. Okay, so from the drivetrain, I think it makes the most sense to look at the intake next. Let's see. Oh yeah, we will leave. Let's try with that first. Okay. Okay, so we can look just kind of where the intake is mounted and how they're integrating some of that into their robot. Relatively simple. It's actually a really nice and clean way to do their intake. It has a single shaft running down here and just a wheel up at the top middle with some belts driving the lower shaft, right? So they're going to drive the upper shaft from this motor here. So this is a Neo motor. It's getting driven by belt and pulley. Spinning this wheel, spinning these pulleys off to the side, and then driving this wheel and this shaft with 2-inch mechanism wheels on it that are going to slide the ball across the bumper and then in through that gap in the bumpers, which bumpers are somewhere in here. Maybe. Okay, let me hide the other stuff and leave the bumpers in place. Okay, so the bumpers are helpful so we kind of see what's happening. When this extends, which we'll look at the pneumatic linkage in just a second, we get those wheels coming out here and able to suck the ball up and in to their robot nice and clean. A couple cool sort of design features that quite a few teams have started doing a lot more of is their pneumatic links. So they have their pneumatic cylinder here and one on the other side, and this is how they deploy their intake. You see that it's actually extended when the intake is closed. So this is the starting configuration, right? The intake and all the wheels and everything are fully inside the frame perimeter, even though this imported with it in sort of the wrong direction. That's fine. Fully in frame perimeter. And so when they actually retract this cylinder, and the air pushes in from this end and pulls this down, then the intake is able to deploy out. Yeah, I assume that wasn't going to work. So I don't have it all set up and mated to where we can animate it all. But the intake's going to deploy out. This roller is going to be sitting kind of right in front of this bumper area. This will tip forward, and so will this. And one of the big advantages of having your intake deploy when your pneumatics retract is it makes it much harder to bend this rod. So that's one of the most common problems that a pneumatically deployed intake can have sometimes, is if you get if a robot drives into you really hard from the side or something like that, or tries to just kind of hit you somewhere with your intake deployed and gets you at a weird angle, some of the forces that are coming back eventually through this cylinder may want to try to bend it. And it normally is worse when it's extended, because that normally means you have a bigger lever arm, or you have parts of the intake are further outside of the robot. So that force is kind of amplified as it gets back towards the cylinder. And a lot of times you'll see these bend a little bit, and that may cause it to not deploy properly. It might just be slower. It might completely get stuck down or stuck up because it's bent so bad that it can't move anymore. So designing it to where it pulls itself in when the intake goes out of frame is normally considered to be a better methodology to prevent that bending. A couple of the other things they did, they have these big mounting blocks here that are pivoting in 2 dimensions. So you have it actually on a ball joint. So if there is some sort of funny load, sometimes that ball joint can help prevent bending too, because you're not able to. It's able to wiggle out of axis a little bit, compared to just using a normal clevis or like a through bolt or something through the back of the cylinder. You're less likely to bend or break the cylinder doing something like this as well. And you can see they did the same thing with the rod end up here. So this whole panel, if this isn't straight or if the robot gets bent out, these can all kind of get misaligned a little bit, and the cylinder still shouldn't see as many bending loads because they're not rigidly mounting in 2 dimensions. Okay. Let's see, a couple other things they did. They have their intake pivots designed into their chassis rails. And so it may be even that they were designing the pivot specifically to mount to holes that they already had on their chassis. Like we don't know which one came first just from this version of the CAD. But because of like the multiple different options here, it's very possible that they just knew they were going to mount they were going to design an intake to kind of fit into this space. They designed all of these holes, they designed all of these holes, and they worked out the geometry and the locations of where they're going to put them on the polycarbonate intake arms, where everything's going to mount, to let the intake work with some already pre-done geometry, right? So this lets you, maybe you decide you want a different intake entirely, you can swap entire intakes and then just figure out new mounting based on the holes that you have to get something that works with the idea that you have moving forward. I believe this is going to be a similar setup. So they didn't CAD some of it, so like we're missing a bolt or a nut here probably. Yeah, so that's just a spacer and a bolt going through it. And so that, yeah, that is what it appears to be. Okay, yeah, so that's spinning directly on the bolt with a bushing there. They space off the rest of it, so this, so the intake panel itself can't slide anywhere. And there's going to be a nut on that side on the real robot. And that works for most likely both of these setups too. Yeah, so there's a bolt going through there as well. Or that's actually yeah, something like that. I don't know exactly what they did here. Oh yeah, so there's another part that they have made that allows this to get up to the right diameter for this part that they're using. Cool. Okay. Yeah, so that's the intake linkage. I imagine they went through and did quite a bit of sketches and things. We don't have the full SolidWorks model. I believe they're in SolidWorks. We just imported the steps, so we can't go through and look at exactly how they designed everything. We can get an idea of what they're able to do. So this comes out and doesn't sit flat. This actually like angles out a little bit. So this is a offset 4-bar or non-parallel 4-bar. So as it deploys, they figure out the exact angle and geometry they want. So the position of where these wheels are, the position of where this top wheel is, and it allows it to intake the balls really smoothly and cleanly. Couple noticeable things. We have like the shape of this, these plates right here that hold this top rail and bottom wheel, or top and bottom shafts together. This is largely so it's out of the way of the ball. So as the ball's coming up, it's able to touch on these belts and keep touching the wheels without touching the the static plates here. So you get rid of some potential jam points or anything like that when you kind of cut these further back and expose just the wheels and the belts. What's the last thing? So last thing, because they're running the Neo, they have the motor controller mounted up next to it. So that lets you have a shorter run for your 3 wires going into the Neo for motor power, and then also your encoder cable. And then this just has to get powered down to the PDH and your CAN wires to connect into there as well. And more than likely, this probably doesn't ever leave the frame Even the motor may not leave the frame by very much. Probably doesn't leave, especially doesn't leave over the bumpers. So most of that's all protected. It's going to be relatively hard to come in and hit that or break that and make it so they're not intaking in any match. All right, looking forward, we're going to get into their ball path and launcher up next. Let's hide some other things. Oh, actually, that can come back because we'll see that together. Okay, so this is kind of their assembly for their ball path and launcher. They were one of the teams we got our inspiration from because, like I said, they were Open Alliance, so they were kind of designing this S-curve along with quite a few other teams, probably a little bit before we moved to it. During the season for us, we were looking at having a turret for a while for the first couple weeks. And then once we decided to not have a turret and we kind of shrunk the size and tried to figure out exactly what we wanted, this kind of became the prevailing solution for quite a few teams, was having this kind of roller here, feeding the balls up along this and then out through a pretty big arc along the back and a lot of contact time with your launcher wheel to get out. And I know that they had multiple revisions of their launcher and hood design and hood rollers throughout the season as they were upgrading things. But I believe this is the final version to my knowledge, but they may have changed things since this was published. So a few things about how they designed this. So the main thing is that these are designed with very large sheet metal parts as kind of the main structure of this entire assembly, right? So you have this part here and you have another one on the other side. And these are providing the main geometry and the main structure for this entire feeder and launcher assembly. So there are some good things with that. It's that everything's kind of integrated. You can package things very nicely. But you do lose some of the ability to potentially change some things, right? So if you ended up realizing, oh, we messed up and got a belt distance wrong, or if you just needed to reconfigure how this roller was going to work, it would be pretty hard to do that without changing the entire assembly, since everything's all mounted into one piece. But it does allow you to be, most of the time it's going to be very light because you don't have to connect a lot of different parts together. You have potentially fewer fasteners. And if you're going to just change the whole assembly anyway, this very well might be the best way to do it and integrate everything together. And that's what they were able to do here. Let's see. So they actually have a second feeder wheel. So kind of just the genericness, or we can go through kind of how the ball moves through the robot. So they have a feeder wheel here. So there's another Neo and belt. So this is one of the most common ways that a lot of teams have started just doing most of their mechanisms. Pretty much how all of our mechanisms work on our robot is if we can just have motor with a pulley on it as a pinion going to a big pulley down here spinning a shaft. That's our ideal scenario. This is like one of the lightest ways to get useful robot motion into your robot, especially if you're just moving a ball. This works really well. You don't have to design a gearbox. You don't have to like package in any of the planetaries or anything like that. You can just get the right belt, make the right pulleys, often printed, and then you can just move along and have a nice simple package that works really well. And so these are spinning 2 mechanism wheels. These are probably here to help make sure that the ball is coming in centered. So these are going to kind of shift the ball to the center. And they run into the second feeder wheel here that's going to actually move the balls up and into the launcher. So this allows them to kind of sequence things, get things in the right spot so the balls are aligned in the right way. We can start seeing a few different sensors. So these are what these yellow tubes are here. These can identify where the balls are. So if the ball crosses in front of this one, you can have a ball here. If the ball crosses in front of this one, you have a ball up here at the shooter path. There's also this little black box right here is a color sensor. So they're able to determine the color of the ball. They have it mounted here. So this very well is likely for deciding if they need to like shoot the ball out. If it's the wrong color, they can spit it out without scoring it, that sort of thing. They also have another one of those assemblies down here. so they can check the color of the ball early and maybe spit it back out the other way. Just kind of depends on how they have it all programmed and whether they kept both of these sensors on the competition robot, were using them, or anything like that. Moving up the ball path, so the ball's been spun on this roller. We now have a main sort of flywheel here. These are all just the Andy Mark Stealth wheels. The 4-inch ones, these are the same type of wheels that we used on our launcher too. They work really well for a game like this where you just need to spin relatively fast. You aren't too worried about how much energy you're actually imparting on the ball. If anything, this year you wanted less energy on the ball. You didn't want to be shooting the ball extremely hard. And you didn't want it to be spinning a lot because you wanted it to just kind of settle into the goal and stay there. You didn't want it to bounce out really easily. And the way the balls worked, these gripped the ball well enough, and they worked well for us, and it seems like they worked well for them as well. They had both of their launcher motors. They did something that we didn't do. They mounted both their launcher motors really far down, so they pulled almost all the way to the base of their robot. And they just have longer belts running up to the side pulleys here. So this, the main reason for this is it's going to get you a lot of, it's all that weight, right? The brushless motors are definitely lighter than motors we used to have, but you still get that weight much lower, so it helps lower the entire robot center of gravity. The belts don't weigh very much at all, neither do the pulleys, but that motor is going to be the heaviest part of that system, so getting it lower, getting the electronics lower with the Spark Maxes down here, it lets you have less wire running up. Just a lot easier to do if you can to pull everything down, but it does come with the trade-off of making sure that you get that belt tension right and that belt spacing correct, because you don't want this belt to get loose at all or be over tight, because you might have it start flapping around or just losing energy from the motor that you would rather have being controlled and consistent going into your flywheel so you can make every shot. But if you can do it right, like they were able to do this year, or they were able to at least make it work, it's definitely a design option that you can use. I think 125 in 2020 is another example of this, where they try to put a lot of their motors low and belt up to their launcher. Yeah, so it's kind of the standard setup coming out. And then the last part, which is one of their newer additions, was their hood rollers. So this is the back side of the launcher compared to like the main flywheel. They have more Andy Mark Stealth wheels. These are the 2-inch versions. And then they have a Rev Neo 550 motor that's actually powering those. So it's powering this pulley down here, driving this. And then we have pulleys and belts on this side, driving up here. And both these are going to be spinning in the opposite direction as this main wheel. And this lets them control spin on the balls at exits. And again, allows them to put less energy in the ball to have it still go the same distance, but have less rotations and less spin, so it doesn't bounce out of the goal. At the same time, they were also able to have an adjustable hood. So we have another Neo 550 here, and a Ultra Planetary from Rev. So this is a tiny planetary gearbox that allows you to get a pretty big reduction in a small space. Then they have a 3D printed pinion gear and rack that is curved, so they're able to do the hood. So this is a pretty standard way to do it this year. There were quite a few teams that were doing this. I think they actually, yeah, so this golden piece in here, more than likely, is a sheet metal part. So this is a metal gear that was laser cut for them, and these two outer pieces are going to be printed. So that gives you a little bit more strength. It lets you mount through it a little bit more, add some rigidity because you have this full aluminum piece in here. And it's very likely, and if you're worried about like teeth skipping or anything, having something like this would definitely help. You would, even if you started cracking something off to the side, a lot of that load could go through the aluminum ones, and at some point you would have to be probably breaking the printed gear before you ever broke the aluminum teeth. But even something like this could probably be done without the teeth. So if you only had a router, you could probably route this same part and just ignore the teeth here and probably not compromise all that much. You could leave those teeth out, but you would still be getting some of the rigidity and strength, depending on how you want to print it. Maybe it would allow you to print it out of something a little bit lighter, or you know, maybe it's not fully carbon fiber prints or something, so it's not as stiff. You could definitely still do that and stiffen it up with aluminum later, and it would still work, or you know, during assembly, and it would still work. Let's see. Okay. Yeah, and so everything else looks like a pretty somewhat normal hood arrangement. They do have like a Lexan plate here. I'm guessing that's what this is in CAD. That I imagine is kind of trimmed up and works differently in real life than it does in CAD. It's pretty hard a lot of times to CAD a lot of these like very specific details of how things are going to get cut off, especially if they're just done by hand a lot of the time just to make something fit. Same way it's kind of coming over on top of it here, and you see it like going through it. That wouldn't be happening in real life. This panel is almost certainly just in front of it, and then as the hood comes up and comes back, this is just that extra space for the ball to ride on as they're tilting the hood forward to get a lower launch angle out the front. So as they get farther away, they can lower that launch angle. If they get really far up close, they can shoot really steep and into the goal. Okay. I think that's most of that. They have a couple different Limelight mounts. I'm not sure if they actually used both at the same time, but it's possible these were just different options. So they have a higher one extended, separate. Maybe they were worried about defense driving in front of them, making it so they couldn't aim. They were able to mount one up here. This is actually a really cool mounting system. My guess, I don't have the material properties and everything, but my guess is these are probably carbon fiber rods or some other light rod. Some teams might use fiberglass or something. Carbon fiber gives you a nice stiffer rod, so it's not going to wobble or anything. And so one of the issues with any sort of carbon fiber, fiberglass, anything, you normally don't want to drill through it like you would in an aluminum tube. So you have to find some way to often clamp it. So I believe that's what these 3D printed blocks are for here. So if we make transparent, yeah, so all they do, they just have a pocket for this rod to be in here. And then as they tighten it down, it just squeezes this between the 3D printed part and this plate, and it clamps it, and so you can't pull it in and out anymore. And without having to drill or glue or puncture or do anything to these rods, you can get them mounted to the robot nice and cleanly, nice, smooth, clean look. And then they do the same thing up here into this part. So this part is actually really cool. So they design it with just this little like kind of figure eight. So there's two little pockets where the rods can go in just at the ends. And they have these internal bent parts. They have a counterboard hole here for a bolt and a nut pocket on the back. And so as you tighten this bolt, you're just going to squeeze these two inner walls together, thus clamping those two carbon fiber rods on the outside. And you get a nice, sturdy, rigid assembly to mount up your Limelight vision system at a nice high point on your robot while keeping everything super lightweight. The carbon fiber rods don't weigh that much. The 3D printed parts don't weigh that much. This appears to be a bent piece of just pretty thin sheet metal, probably, to keep it rigid going across this like whole span. They probably just use a piece of sheet metal to do that, so you don't get very much flexing up there. And so that works out really well. I don't think there's any other major details in here, just a lot of just kind of using the structure to help mount just the required parts of the robot, network switches, maybe a Raspberry Pi or other type of computer, radio, air tanks, all of those sort of things. There's some other nice 3D printed parts here that help mount that Lexan panel on. So these were printed kind of matching the shape and geometry of this outer aluminum sheet metal part with nice nut pockets and things for this polycarb part to mount to. Some more 3D printed parts that help mount all the accessories. So a lot of really cool design details. These are just like zip tie places. So you just run the zip tie through these slots and through these little holes. And you get a really nice, robust place to mount your motor controller that just clips onto their tubes of their S-curve. I think that's most of it. Yeah, we see another camera system here. This is probably their driver cam. Maybe a Raspberry Pi mount in there too, or something like that for a nice wide angle fisheye driver cam. A couple things, I think we talked about this down at the drivetrain, but we can talk about it up here too. So even though there was only going to be one motor mount here, and they knew that, it was a lot easier just to make these plates identical. So they have these identical plates that lets them have the motor mounting on this side if they wanted to. Maybe something happens over here, they're able to move it all over and still make it work. It also just is the weight's not worth the effort most of the time to get rid of this, when potentially you can have it as your spares get easier. You have the same part, you only need like 3 of them or 4 of them, and you can still swap out spares really easily if you need to. And the other part I just noticed that I forgot to talk about is up at the front of this plate, they have gear teeth running here. And so this isn't to move the hood, right? Because the hood movement is all happening back here on this gear. This is driving it up and down. But this is here so that they can know the position of the hood. So they want to know exactly where it is and at what angle it is. So they have these gear teeth. Inside of this should be another gear here. So we have another gear that's mounted into 2 bearings. So we have bearings there and there. And so as the hood spins, this gear rotates. And right here, mounted on the outside of their shooter plate, is a what's called a rev through bore encoder. So this hex shaft going right here is just spinning inside of here, and they're able to get an absolute position of their hood through this encoder if they want. So right at startup, doesn't matter where the hood is, they can know exactly where it is, forward, back, anywhere in the middle. That's my guess is how they're doing it. It kind of depends on the gearing to make sure they can get an absolute position, because this can only tell you absolute on 1 revolution. But that's most likely what they're doing there, so they can know exactly where the hood is. Even if something reboots during the match or anything, they can still know where the hood is without having to rehome it or reset it or anything like that. Okay, I put a little bit longer into some of this than I wanted to, but I want to get into the climb, because that's one of the reasons why we're here today. Okay, so let's look at the climb. Okay, I guess the last thing, so yeah, we have these last sort of protectors here. This was probably just to help keep balls out of the robot, things like that, other people out of the robot, and teams as well. So if you don't want a spot where a ball might be able to balance and get caught, you also don't want anybody else's intake to come jamming in and hitting belts or anything else. So you have to put up some walls and protection to stop anything like that from happening. Okay, so what are we hiding? We're gonna hide kind of that main assembly and let us still look at the climber. Oop, not that one, that one. Okay, and this one. Okay, so let's look at the climb and how it's mounted to everything. So this was in my opinion, one of the better well-done climbs. So they were able to kind of design and configure this full solution during the season. So they were able to see some other really good kind of examples of the same type of setup. Quite a few teams moved to something like this throughout the season. And it gets them a very, very fast and efficient way to get a high climb with very little weight, very little space, and let it work very, very well. Right at the end of the match, they can come in, kind of get a high, and get those extra points, even while their 2 partners are on traversal or anything like that. And it's a really simple, easy to potentially build mechanism. So let's talk about what it kind of does first, and then we can look at the details of the functionality. So basically this this hook up here and this extension is a 1x1 aluminum extrusion inside of here. So this is going to work kind of on the same principles as pretty much every telescoping climber, telescoping arm, pretty much works in FRC throughout history. The designs have kind of all gotten, there's been a lot of evolution over the last couple years. Quite a few vendors came out with different COTS versions. There's an Andy Mark one, a ThriftyBot one, a West Coast Products one. There are a bunch of different ones. So a lot of people were able to take kind of all the ideas that were put out through those COTS versions and through a lot of other people's robots that have kind of been building them over the last few years that we've had climbs, and gotten a lot of inspiration on how to make them nice and easy and in a whole variety of different manufacturing methods. So I'm going to hide this main outer tube. So it's kind of the main structure of this whole assembly. Is you have this main outer tube that should be about 2 inches by 2 inches, and the inner one's about 1 inch by 1 inch. And we can see kind of what's going on inside of here. Actually, let me make it transparent so we can kind of know what's happening. Okay. So inside of here, we have this 1x1, and that's kind of the main thing that's actually doing all the motion, right? So this is just moving in and out, extending up and down so that they can grab on to the mid bar and pull themselves up. And so while you're doing that, you want to make sure things are rolling or sliding really nicely. So that's what these bearings down here are for. So they have these 4 bearings, 1 on each side, and those are running and rolling along the inner walls of that outer 2x2. So they're going up and down. So using the bearings is one way to do it. Quite a few teams have been able to do the same idea, which is just remove some of the friction and stop the jamming, just using different types of plastic sliders. Delrin, also known as acetal, is one of the most common. It has a very low coefficient of friction. It's a very smooth, slippery plastic. So if you get it to be the right shape and size, and you kind of wrap it around this inner 1x1, you can have it just slide up and down on the inside. The alternative is what the Rembrandts did here, is you build in a bearing setup. So instead of just having that sliding motion, which is normally going to have a little bit more friction than a rolling motion where you have nice smooth ball bearings rolling, they were able to set up and do ball bearings. And we can look a little further. I'm going to go ahead and hide this because we're going to need to look at this box right here. Go ahead and isolate. Okay, so this is a really cool part. So this is almost, my guess is this is 3D printed. It's possible they did this. Maybe not. This might actually be aluminum. Depends on what they ended up doing here to be able to. Did they tap those? Or those are just nuts on the other side. Yeah, those are bolts going in. So I'm not sure if they just tapped into the 3D printed part or if they actually tried to make this out of aluminum. That I don't know. And it's not something that's easily be able to define from CAD. But largely, this is just setting up how this is going to mount into the 1x1 square tube. So that's what those 4 bolts are. Or I guess 6 bolts, because there's one on either side here as well. And then the bearings themselves, they do have the little slots cut out in there, but they're actually held in place by this lower block. And so this one has a lot more detail into it and is probably routed. And we can know that because we have these dog bones here. And so these allow the router, or potentially end mill if they did it on a mill, anyway, a small rotary cutter to cut out this path and give you like a sharp edge here where you're going to stick a dowel rod. So you're going to have just a cylinder of steel, little dowel pin that's going to go in between here, and that's what the bearing itself is going to ride on. So it's going to be rotating on. But because we have these dog bones, we can tell that there was some rotary cutter that came in, then it cuts out to this outside and cuts completely flush back to here, and then cuts again. So that gives you that full width here to be able to put that dowel pin in, because if you just had a rotary cutter come in and just cut out this way, it wouldn't work so well. And if it was 3D printed, you wouldn't need these dog bones, because you could just print it. You could print a flat corner or something pretty close, right? You might have a little bit of a relief because the print does have a little bit of a radius, but you wouldn't have to do it nearly as much as a full, like radius, so like a 0.08 inch cutter or something like that. So yeah, pretty small potential cutter if they're doing it that way. It also might be printed. It might have just been how they're designed it. That would be hard to know, but more than likely it's probably cut with a mill would be my guess, but we also might be wrong. So if whenever the Rembrandts eventually watch this, they can let me know. Right, so then this is bolted up through that into this part here. So yeah, so both of these are almost certainly going to be made out of aluminum is my guess, because you have enough stuff being threaded into it in different ways that if you printed this, that would be pretty tricky to have the strength of those threads not want to be pulled out. So this bolt going up through just like a through hole here, and then threaded into and securing up into here. There's probably a way you could make this printed, and depending on how much you trust the threads and what screws you use and things, it's very possible this could all be printed without causing too much issues, because you're probably not supporting too much of the robot's load on here, right? So the way that you're actually climbing is you have a rope wrapped around this spool that's winding and unwinding to do the climb. So when it's fully wound in, the hook's all the way down. As you release it, it lets some of that rope go. And you're normally going to have the rope run all the way up directly through the center here. So that's what this center hole is for. So that's what that center hole is for. And so the rope's going to run directly up and is normally going to be mounted somewhere on the hook. So that's probably, my guess is what this standoff and bolt is for, is you're going to wrap the rope around here. So when you're actually doing the climb and you're pulling down, the load goes straight from the hook assembly out here, straight into tension into the rope. So none of the bolts or rivets here that are mounting the hook on, none of this tube, none of that is seeing any of the real force of lifting the robot. All of that is coming through the rope and going straight down to the spool itself. And all of those can definitely handle the weight without doing any sort of bending or pulling apart or anything like that. Okay. So looking forward, we just look at the bottom bearing assembly. So we're going to look at the top real fast. So we have a similar thing going on the top. So this is moving up and down. So then at the top of the 2x1 up here is where we have our stationary bearings for the top half. So as everything moves in this telescoping assembly, as it starts extending, these lower bearings start moving closer to the top bearings. And then when they pull back down, the lower bearings start moving further away. And everything stays supported and keeps this tube moving in a straight line. So if we didn't have those bearings there at all, it'd be very easy for this to wiggle around, especially as you started getting really close to the top. It might be leaning all over the place. We wouldn't want that. So this is a rather simple setup. So we have these two plates, one on both sides, and it has a similar cutout to the lower one, and we can see the dowel pin directly here. So we have this dowel pin, again with those kind of like dog bone cutouts, so that they could do this on a mill or a router. And then they have holes, the full cutouts for the bearing assembly itself. And they actually just use these flange bolts to hold in this dowel pin. So if these bolts weren't here, this whole bearing assembly, all three of these parts, could just fall out. But these bolts are here, overlapping on that flange right there. And that stops the it stops this assembly from falling out, and it also stops any of the load. So if this whole square tube tries to push out to the side, it pushes against these bearings, they push against these bolts, and it keeps it straight. And that's the whole idea of these bearings, is to keep it sliding up and down nice and smoothly and keep it in a straight line. So the same thing happens on the other side. And then for the kind of front and back motion of the hook assembly, so that it can't lean forward or backwards, we have these two larger bearings on both sides. And this is important because they're going all the way kind of to the edge of the tube. So they're going to be on the strongest part of the tube. So they're riding right on this edge where they're not going to be able to like bend in or deform the tube at all. So if instead of having these two bearings out here, maybe you just had a single bearing riding right in the middle, it's very likely that if you tried to like hang the whole robot from that, you'd start bending in this edge of the square tube. You'd start making this a big radius right here, potentially even breaking it. But because they're able to support it all the way to the edges, it's much harder to break anything along this whole face, right? Because you have this whole big line of aluminum that doesn't let it bend or move or do anything. And this is definitely this is the direction that's going to take more load, because that's normally just the way the robot's hanging and swinging, and anything like that is that forward and backwards. There's definitely going to be some side load because they only have a single hook. So there is going to be some side load one direction towards, the weight of the robot. The center of gravity of the robot's somewhere over here. This hook is going to be trying to swing in, or I guess this is going to be trying to swing under the center of gravity, kind of depending on how it's going up. And so, yeah, you would definitely see some pushing in on these bearings, but it might not be enough to break anything. Some of that's just depending on how you build it, how heavy the robot is. All of that starts coming into play. Okay, so finishing it off, the hook assembly is easy, just a couple pieces of aluminum and the 3D printed part, most likely here, that just gets bolt through. And then so the way they convert this into a high climb, because this is kind of just your standard way of getting up into the mid-bar, is with the pneumatic cylinder here and the extra arm and latch. So this arm, once they're up on the mid-bar and they pull themselves up, this pneumatic just extends. This arm right here goes up and latches onto the high bar. So the high bar goes through these two fingers that are, can't tell in CAD, but most likely spring-loaded. I also don't know what this part is. This maybe should be something hanging out in CAD. It may not exist at all. But these are spring-loaded little fingers. So as the bar comes through, it can't pass back, because if you try to push on this, right, this bolt hits the side, so you can't push on it at all, but you can push it forward because this bolt's going to go out. And so if you have like a rubber band tied from here back to somewhere back here, you can imagine that you'd be able to push this in but not push it out. And so that's the whole idea, is it snatches and grabs onto that high bar really quickly. And then as you lower the winch assembly, so as you run this motor backwards from, or like extend it again, you're now latched onto the high bar, you unlatch from the mid bar, and you swing off the mid bar, and you get the points for the high bar. So it's really fast, really quick and easy to get those points. I don't think anything in there is too weird or complicated. They just have, yeah, everything's just kind of aluminum plates bolted to aluminum extrusion. A few more bolts going in. Yeah, this plate, these plates up here, that's what we didn't talk about. So these plates up here, for the lower part of this, these are just clamping around the tube, because they can't go and have like a bolt right in through here, through the middle, without potentially interfering and rubbing, or especially if you wanted to bolt all the way through, you would definitely interfere with this tube sliding in and out. So anytime you do any telescoping things, you have to remember that you can't put any bolts through the middle of this, unless you design it really well to be off to the side to where you have enough room. Or sometimes if you get it in ahead of time, you could potentially put like a bolt from the inside going out to where like the bearings aren't rubbing or something, depending on if you know exactly where the bearings are running. You might be able to do something like that if you look at the design, but you still have to be careful of where things are on the inside of that tube, since you have the bearings or sliders or something like that going up and down them. So these out here are just here to clamp these parts together to keep this whole thing stiff. And then it's actually mounted up at the top here in the same place that this plate is mounted. So you have these 4 bolts on either side, mounting this whole assembly in through the rectangular tube into these plates. And you get your whole climber assembly fully done. I didn't take too long on the power system for this, but we can do it really quickly. There's not much to it. They basically have a Neo going into a Max planetary. They did some custom work to add in a brake. So they have a pneumatic cylinder up here, so that's what this little thing is. It's a short stroke pneumatic cylinder. And if I make this transparent, you can see what it happens is when air goes through this port and extends the cylinder, it's able to drive the end of that cylinder into all the little gaps in these little plates that they made. And so that completely locks the mechanism, and so it stops it from being able to release or go up or down. It's just a full brake right at the motor shaft. And that's normally the best place to do it because you get even that extra gear reduction from this gear stage here. So this is reducing the speed of the motor before going onto the spool. So this is either a 3, 4, or 5 to 1 max planetary reduction. And so you get all that force amplified, all that holding power. So it's even easier to hold the robot up and not let it fall back down. So they would only be really using that if they didn't get the mid bar, or if they didn't get the high bar latched and they wanted to make sure they could stay on the mid bar and not go back down, like if it was going to go more than 5 seconds, they could have the brake deployed and make sure they can stay up on the mid bar. And then on the other side, they have another one of those through bore encoders. So they have the hex shaft right here going into this encoder, so they can tell the position and velocity or anything else, depending on how they want to program it, of this shaft and know how the spool is spinning. And so they can better program their climber with that plate. And then the whole climb is rather easily mounted just with the angle bracket here, and that's what's holding it to the main drivetrain, and then it also mounts over to the shooter assembly in a couple places, so I'll bring that back in. So it gets mounted here along this edge. Then they have a sensor as well that they're able to use to do some more programming of their climber so they can tell when it's fully down. My guess is probably that they're using this to make sure that they deploy the high bar hook at the right time, right? They want to be pulled up far enough onto the mid bar so that when they deploy the high bar hook, it actually hits the high bar. They don't deploy it too early. And they also have a few of these 3D printed clamping blocks, and these clamp the whole tuba structure to this main side frame. So this is important so that this whole thing doesn't try to just like peel the robot or try to bend out to the side. It's all clamped to the superstructure up here. And so their whole climber assembly gets support from their shooter assembly, but then their shooter assembly also gets a little bit more rigid too, because they have this whole big tube sticking up the side now and clamping it to there too, so you can't get any bending or anything along this plate now, since this is stiffening it up as well. So I think I covered just about everything in this robot. And again, it does a lot of detail in a very tiny package for what they were able to build into such a small robot, and basically do almost every part of the game. Right? It never got the traversal climb, but that's definitely not needed. There are teams who made that strategic choice to just do the high climb, and you're able to get the ranking point and win a lot of matches just doing that, and it worked very well for them. And the Rembrandts had a really good year this year, and kind of designed in and honed in on a really nice design philosophy throughout their whole robot. All right, so that's all we have for tonight.